Hello friends, we will discuss the equilibrium reactions in acid-base chemistry. As you know, in the Bronsted-Lowry theory of acids and bases, this theory, it describes acidity in terms of protons, that is a positively charged hydrogen ions here. A Bronsted acid, it is a proton donor, and a Bronsted base, it is a proton acceptor here. For the acid to donate a proton, it should contain a proton. That is, it must contain a hydrogen atom. Okay, the acid general symbol is Ha here, and a base, the general symbol is B. The base must contain available electron pair. Okay, electron pair, it can be a non-bonding pair of electrons, or it could be a electron pair in the pi bond here. Okay, therefore, base must contain available electron pair that can be easily donated to form a new bond with the proton here. Now, the reactions involving the transfer of a proton from an acid to base, that is a main reaction. That is, an acid and a base, they react and a proton is transferred from the acid to the base here. Okay, these reactions are proton transfer reactions here. Proton transfer reactions here. Now, this can be represented in this fashion. That is, one bond is broken here. That HA bond, it is broken, and a new bond is formed. HB bond is formed here. Okay, the electron pair of the base B, it forms a new bond to the proton of the acid here. Now, acid HA, it is losing the proton, leaving the electron pair of the HA bond on A. Correct. Therefore, loss of a proton from the acid forms its conjugate base, and gain of a proton by a base forms its conjugate acid. Okay. Now, we are using a double reaction arrow. That is an equilibrium arrow. Double reaction arrow, it is used between the starting materials as well as the products here to indicate that these reactions can proceed either in the forward direction and reverse direction. That is the equilibrium reaction, we can say. That is, it can, either the reaction will be favoring the formation of the products here, or it will be in the backward, the reverse direction. That is favoring the formation of the reactants only. Okay, they are equilibrium arrows here. Now, the essential principle in the case of the Bronsted-Lowry acid and bases, it is here the removal of a hydrogen atom, that is a proton, from the acid, it forms its conjugate base here. And addition of a hydrogen to the base forms its conjugate acid. Okay, therefore, this Bronsted-Lowry acid-base reaction, it always involves the transfer of a proton from an acid to a base. Correct? Acid to a base. Now, we can say, and when this equilibrium reactions, we have always defined the concept of an equilibrium. That is, equilibrium reaction, an acid HA, and it is reacting with water. Acid HA. So, when it is reacting, we can visualize a reaction of this nature here. Water here. So, acidity. What is meant by acidity here? Acidity means acid strength, the strength of the acid. Okay, strength of the acid means the ease with which, the measure of the ease with which an acid can donate a proton here. That is, the more readily a compound, it donates a proton, the stronger the acid. That is the concept here. Now, it is measured using an equilibrium constant. Okay, acidity is measured in terms of an equilibrium constant here. That is, when an acid, HA, it is dissolved in water, an acid-base reaction takes place here. That is, a proton transfer reaction takes place, and an equilibrium constant K can be defined for this one. It can be written for this equation here. Okay, so the reaction will be as usual. That is, there's a lone pair of electrons here. This lone pair will take this proton here. Okay, this. Correct? Like this, the equation will, the reaction will proceed here. Therefore, the products formed will be the conjugate base plus the conjugate acid here. The conjugate acid will be S3O plus. This is the hydronium ion. Okay, this is hydronium ion. So, this is the equilibrium reaction taking place. The acidity is measured by the equilibrium constant. Now we can find that, acid HA dissolved in water, acid-base reaction is taking place, and an equilibrium constant K can be defined for this thing. So the K, equilibrium constant K, we can say that is the products, the concentration of the products divided by the static materials, concentration of the static materials. Okay, so this is KEQ, that is the equilibrium constant here. So I will just change this page now. So here, how will you write this equilibrium constant here? That is KEQ is equal to, that is the concentration of the hydronium ions here, that is the product, then the concentration of the base, conjugate base here, divided by HA that is concentration of HA, that is the starting material, into water. Now the concentration of water, it always remains constant here, and therefore we can define an acidity constant Ka. Acidity constant Ka, it is equal to H3O plus, that is the concentration of hydronium ions, then this one divided by starting material HA. Okay, so you are familiar with this concept here. Therefore here Ka, this is known as acidity constant. Acidity constant Ka, it is actually directly proportional to the hydronium ion concentration. That is the acidity here. Okay, Ka is a measure of the hydrogen ion concentration, hydronium ion concentration. Hydronium ion means it is the hydrated proton. Okay, a proton hydrated with water. That is the thing. So Ka, it is a measure of the hydronium ion concentration. So that in turns, we can say it is acidity, is a measure of acidity here. Ka is a measure of acidity. Okay, now let us see this Ka. We have seen this Ka value of organic compounds here. It is a very low. Ka values are very low for organic compounds in the range of say 10 raised to minus 5 to 10 raised to minus 50. That is a very low value for organic compounds here. Therefore, we have defined another quantity, pKa. This is the most important thing, you see. Minus log Ka. It's a logarithmic function here. Okay, pKa is equal to minus log Ka. This is the definition here. Correct? So the larger the value of Ka, the smaller the value of pKa. Therefore, Ka, it is a measure of the acidity. The larger the value of Ka means the stronger the acid. Correct? And therefore, the stronger acid, when you are converting into the logarithmic function, it becomes the smallest value or the smaller value. Okay, the larger the value of Ka, the smaller the value of pKa. Correct? Therefore, pKa values of typical organic acids will be in the range of say plus 5 to plus 50. So this is the pKa values of organic compounds. That is smaller number, stronger acid. The smaller the value of pKa, the stronger the acid here. So increasing pKa value means decreasing acidity. You know that. Okay. Then a strong, now you see the understanding the strength, acid strength. Okay. It is the first step to understand the strength of a base and vice versa. That is, first you understand the strength of an acid, then follows this understand the strength of the base here. Therefore, understanding acid strength, it is the first step in understanding, to understand the strength of a base. Okay. Now, so there is an inverse relationship rather exists between acidity and basicity. Inverse relationship exists between acidity and basicity. Correct? Now, a strong acid, okay, strong acid means it readily donates a proton, forming a weak conjugate base. So, these are fundamental things now. Because in equilibrium reactions, these are all very, very important concepts here. Like a strong acid. So, what happened? A strong acid, it readily donates the proton. And what will be the product here? A weak conjugate base. Correct? Weak base. Strong acid always gives a weak base. Correct? A strong base, it readily accepts a proton, forming a weak conjugate acid. That is strong base. This is, it readily accepts the proton. Okay, that is a characteristic. Strong base, it readily accepts the proton and it is forming a weak conjugate acid here. Okay, now the negative value of pKa, it indicates a very strong acid here. That is, the smaller the pKa value, the stronger will be the acid. Okay, now the increasing pKa value means decreasing acid strength. Okay, so these are the fundamental things now. Now let us see, in the case of base, what will be the situation here. So base means a strong base. Acids have weak conjugate bases. Okay, strong acids it will always give weak conjugate bases. Okay, now weak acids, strong conjugate bases. It will give you, weak acids always give you a strong conjugate base. Okay, so this is the relationship here. That is, strong acid, it always gives a weak conjugate base, and a weak acid always gives a strong conjugate base here. Okay, strong acid, weak conjugate base. Weak acid, strong conjugate base. Okay, now just like acids, the bases are also can be classified as a strong base and weak base and all this kind of thing. Okay, now the relative acidity of different compounds. How will you compare? The relative acidity of different compounds can be compared using their pKa values. Okay, the acidity can be compared using their pKa values. Now, how will you compare the basicity? That is the relative basicity of different compounds. You'll have to compare. It can be compared using the pKa values of their conjugate acids. Okay, that is the different relative acidity of different compounds can be compared using their pKa values, and the different basicity, that is the relative basicity of different compounds. Okay, relative basicity of different compounds can be compared using the pKa values of their conjugate acids. Okay, now in the case of this one, strong base RNH2, an amine compound. Okay, amine compound, RNH, alkyl amine compound, say HA. This kind of a reaction, if you see, acid-base reaction only. Okay, like this it will go. Now this lone pair proton here, correct? So what will be the type of reaction here? Equilibrium arrows here. RNH3. RNH3, it is the conjugate acid here. Okay, then we get A minus. This is the conjugate base here. Okay, now RNH2 is a stronger base. Okay, the stronger base, and it is giving a weaker acid. Strong base will give a weak acid. Okay, now the weaker the conjugate acid, the higher pKa and stronger the base. The reverse is correct. True. Okay, now we are giving, say RNH2, that is a strong base, it is reacting with an acid HA, and we are getting RNH3, that is a weaker acid, conjugate acid, weaker and acid here. Okay, now we have seen strong base, it gives a weaker conjugate acid. So now in the reverse direction, if we just say the weaker the conjugate acid, the higher pKa value, because the lower pKa means strong acid. So weaker conjugate acid, it is a higher pKa and stronger the base here. Okay, the reverse is correct here. Okay, stronger, the weaker the conjugate acid, the higher the pKa value and stronger will be the base. Okay, now weak bases, they are very, very stable species. Why? Because they do not readily share their electrons to form bonds with protons there. That is why the weaker bases, the weak bases are stable species. Weak bases, stable species means their reactivity is controlled. Rather, they are not that reactive. The reactivity depends upon the availability of the electrons there. Okay, the bases should be ready to share those electrons to form bonds with protons. So in the case of weak bases, why they are stable species? Because they do not readily share their electrons to form bonds with protons there. And on the other hand, the strong bases, we can say, they want to share their electrons to form bonds with the protons here. Correct. That is, strong bases, they readily don't want to share their electrons to form bonds with protons. Whereas weak bases, they are stable species. They do not readily share their electrons to form bonds with the protons there. Okay. Now the strong acids, they dissociate to form weak conjugate bases. That is what we have written here. Strong acids always dissociate to form weak conjugate bases. Now the more stable the conjugate base, okay, the equilibrium, it will be shifted towards that conjugate base. Okay, now we will just discuss the equilibrium reactions here. What are these equilibrium reactions? So equilibrium reactions means a proton transfer reaction So a proton transfer reaction represents an equilibrium that we have seen. That is, we are using a double reaction arrow there. Okay, so an acid donates a proton to a base. It forms a conjugate acid and conjugate base. Okay, loss of a proton results in the formation of a conjugate base, and gain of a proton by the base, a conjugate acid is formed there. Therefore, in the system, there are always two acids and two bases. That is, the first thing is acid base. Okay, it is forming conjugate acid, conjugate base. Therefore, in the system, that is in the reaction mixture, there are always two acids and two bases present here. Okay, so now the position of the equilibrium. That is, position of the equilibrium means whether the reaction proceeds in the forward direction or in the reverse direction. That is the position of the equilibrium. It will depend upon the relative strengths of the acids and bases, because in the system there are two acids, two bases. Okay, now the relative strength of these acids and bases, that is whether it is a strong acid, strong base, and weak acid, weak base, and all, that is the equilibrium will depend upon these factors. Correct. So in a proton transfer reaction, the equilibrium, it always favors formation of the weaker acid or the weaker base. That is the survival of the weakest here. Correct. That is, the equilibrium favors the formation. That it will be shifted towards the right. That is towards the weaker acid and weaker base here. Okay. A strong acid, it readily donates a proton forming a weak conjugate base. You know that. Strong acid readily donates a proton to form a weak conjugate base, and a strong base, it readily accepts one proton to form a weak conjugate acid. Okay, therefore the equilibrium always favors the formation of a weak acid or a weak base here. A strong acid readily donates a proton. What is the product? A weak conjugate base. In the same way, a strong base, it readily accepts one proton, forming a weak conjugate acid. Okay, now these two species, that is a strong acid and a strong base, they react to form a weaker conjugate acid and a weaker conjugate base. And there is no further reaction. Okay, that do not donate or accept a proton any further there. That is the, I will just show it by equation. Strong acid, it will react with a strong base. So what will be the product here? It will be a weaker conjugate acid. That is, these two species, strong acid and strong base, they react to form a weaker conjugate acid plus a weaker conjugate base here. Why it is weaker? Because they do not either donate a proton or accept a proton here as readily. Okay, so this is the basic thing about equilibrium reaction. Now let us see, in an equilibrium of, we can predict the relative equilibrium concentrations. of the acids and bases here, acid and conjugate acids here. We can predict the relative equilibrium concentrations of acids as well as the conjugate acids by looking at the pKa value. So this is the most important factor here. These things we can see in the textbooks and all, pKa values of various acids and bases here. Based on this, we can make so many calculations. Okay, the relative equilibrium concentrations of the acids, conjugate acids and all, and we can find out compare the basicity. So many things it can be done with using this data here. Okay, now in this acid-base reaction, we have seen the general rule, that is the equilibrium always favors the weaker one, the weaker acid and the weaker bases here. Okay, now if you take an example here, the acetic acid. This acetic acid, when it is dissolved in water, correct? So the products formed is the hydronium ion here and acetate anion. Okay, this is the products formed here. Now acetic acid, the pKa value, it is in the range of around 4.75, I think. Yeah, acetic acid pKa 4.75, and the hydronium ion, it is pKa, so it is minus 1.7 here. Okay, now which is a stronger acid here? The lower the pKa value, the stronger the acid. Therefore, the hydronium ion, it is the stronger acid in compared to acetic acid here. Therefore, smaller pKa means stronger acid. Hydronium ion is a stronger acid than acetic acid. Therefore, what will be the position of the equilibrium here? The equilibrium will be shifted towards the weaker one. Okay, equilibrium is getting shifted towards the weaker one. That is, the weaker one is acetic acid. Therefore, we are showing it by using an arrow, unequal equilibrium arrow. This arrow will be longer. That is, arrow pointing towards the starting material here. Here, equilibrium, the starting materials, formation of the starting materials, it is favored. Therefore, this arrow, longer arrow I am putting here, unequal arrows here. Okay, so in this case, the direction of the equilibrium, it is indicated by the relative size of the two equilibrium arrows. So one will be longer, other one will be shorter. The longer one points towards the formation of the weaker products, weaker acid or a weaker base here. Correct. So this is the reaction, equilibrium reaction here. Now the pKa difference, that is one is 4.75 here minus, that is other one is minus 1.7. The difference in the magnitude of these pKa values. Okay, so it is indicative of the extent to which, okay, the equilibrium is shifted towards the weaker, towards the direction of the weaker acid here. Okay, that is the difference in the magnitude of the pKa values. It is indicative of the extent to which, the extent of shifting the equilibrium towards the, or in the direction of the weaker acid. Correct. So this is the basic thing about equilibrium reactions here. Now let us see a very interesting kind of a thing, that is the direction of equilibrium. How will we find out the direction of equilibrium? That is a very important thing. Direction of equilibrium means in the reaction, acid proton transfer reaction, whether the equilibrium is favoring the formation of the products or it is favoring the formation of the reactants here, whether it is proceeding in the forward direction or whether it is proceeding in the reverse direction. That is the direction of equilibrium here. Now suppose we are given an acid here, in an equilibrium reaction between an acid acetylene . Now first we should see which is acid, which is base. Okay, now this is acetylene, a reaction between this is acetylene. Okay, a reaction between acetylene and an amide ion. Okay, that is NH2 minus. Correct? So a reaction between these two species here. We can put a lone pair. Okay, now we have to determine the direction of, we are asked to determine the direction of equilibrium when acetylene reacts with an amide anion. Okay, in a proton transfer reaction here. Now, first we should identify which is the acid, which is the base here. Now, in here, this amide ion, it is having a negative charge here. Therefore, negative charge, that means acetylene is the acid and this is the base here. Okay, so this is the acid. Acetylene is the acid. The pKa of acetylene, it is 25. Okay, this is amide anion. So this is reacting. Which direction the reaction will proceed here? Now we will be getting what is the type of reaction here. That is, there is a proton. This proton, it will go like this. And the electron pair will get shifted like this. Then this lone pair, it will take this proton. Okay. Therefore, this is the way the reaction is taking place here. Now, what are the compounds formed? This is HC. This is the anion formed. This is the acetylide anion. Okay, this is the conjugate base of the acid here, acetylide anion. Then we get the conjugate acid will be NH3. Okay, conjugate acid. This conjugate acid ammonia, it is 38. Okay. pKa 38. Okay. So this amide ion, we are getting it by the deprotonation of ammonia. That is, a proton removed from ammonia, we get NH2 minus. Correct. So acetylene is reacting this NH2 minus here. NH2 minus, there should be one more pair of electrons here. Correct. Then this is forming acetylide anion. That is the conjugate base. Acetylide anion is the conjugate base here. And ammonia is the conjugate acid here. Now we have to compare. Okay, the step 3, what we do, we compare the pKa values. Okay, pKa values of the acid and the conjugate acid here. Now the equilibrium, it will be favoring the formation of the weaker acid and with a higher pKa value. Weaker acid means higher pKa value. So in this reaction, the acetylene pKa 25, ammonia pKa 38. Therefore, the higher pKa value is of ammonia. Therefore, ammonia will be a weaker acid. This is a weaker acid. And acetylene will be a stronger acid here. Okay. Therefore, the pKa of the starting acid, it is lower compared to the pKa of the product acid. That is the conjugate acid here. Therefore, the starting acid, it is a stronger acid here. Acetylene is a stronger acid compared to ammonia. Therefore, we have to see in which direction the reaction proceeds, in the direction of the weaker acid. Therefore, we should put an unequal arrow here. Okay. These two arrows, one arrow will be longer and the other arrow will be shorter. The longer arrow means it is pointing towards the weaker acid or weaker base, whatever it is there. No. So one is longer, other will be shorter. This is how we have to represent the equilibrium here. Correct. See, this is pointing towards the weaker acid here. Therefore, the equilibrium, favors towards the or in the direction of the weaker acid. That is the formation of the ammonia here. with a pKa value, higher pKa value, 38 here. This is unequal equilibrium arrow we have to use here. Okay, so this is how we have to determine the direction of equilibrium. So this is just an example I have given here. So another important concept which we are going to discuss is deprotonation. Deprotonation means remove the proton from the acid. So you are given a base and you have an acid here. You have to find out whether this base is strong enough to remove the proton from the acid here. Okay, so how will you know that? That is whether a particular base, it is strong enough to deprotonate a given acid here. Okay, so that the equilibrium, it will be favoring the products here. Equilibrium will lie to the right side. Correct. Now, let us see. We will get examples here. I will just, before generalizing the principle, we will see the issues or rather examine the, question with certain examples here. Okay, we can examine with we will say whether a particular base is strong enough. Which base we can say that if we will take the case of ethanol. This one I will just OH here, then two pairs of electrons. Okay, so we can compare ethanol and acetylene again. Okay, let us see which we will examine this in detail. Correct. This is ethanol and this is acetylene. Okay, two compounds here. Now we let to see ethanol acid. We can say it is an acid, and this is also an acid here. Acetylene is an acid, ethanol is an acid here. Okay, so ethanol pKa 16, acetylene pKa 25. Correct. Now, ethanol is giving a conjugate base. CH3, CH2, O minus. This is ethoxide. Okay. It is the conjugate base of ethanol here. Now, in the case of acetylene, we have seen the conjugate base is the acetylide anion. Okay, this is the acetylide. Acetylide anion here. Okay, ethanol, the conjugate base is ethoxide, and acetylene, the conjugate base is acetylide. Now, which is a stronger acid here? pKa value 16, ethanol, pKa value 25 for acetylene. Therefore, ethanol is a stronger acid. Okay, ethanol is a stronger acid than acetylene here. Therefore, acetylide, it will be a stronger base than ethoxide. Correct? So, ethanol, it is a stronger acid. Stronger acid, and this will be a weaker acid here. Because pKa 16, pKa 25. Therefore, ethanol is a stronger acid. Acetylene is a weaker acid here. Therefore, acetylide, it will be a stronger base. A weak acid gives a strong base. Okay, stronger base here. Therefore, now ethoxide, it will be a weak base. Weaker base, we are comparing it. Okay, which is stronger, which is weaker and all these kind of a thing. So now we have the system here. Now we will have to see proton transfer reactions. How the protons are getting transferred. Reaction we will have to see. Now, two types of reactions we can see here. Ethanol reacting with acetylide. That is, ethanol is an acid, acetylide, it is a base. Or acetylene reacting with ethoxide here. Okay, acid-base reaction. Now, one reaction we can see which direction it is proceeding here. Whether this base is capable of or strong enough to deprotonate. That is removing the proton from the acid here. Okay, so this is our acid, acetylene, acid, pKa25, we know that. So it is reacting with the ethoxide, that is the base. Now, what will be the products form? Arrow length and all we will adjust later. So let us see how the reaction is proceeding. Here in the case of acetylene, so we can say this goes like this. Then this electron, it takes this proton here. Okay, so this is the way the reaction is proceeding now. Now what are the compounds being formed? That is acetylene, when the proton is going, the conjugate base of acetylene, that is the acetylide anion, we know that. This compound is formed, conjugate base, acetylide, conjugate base. Then we get ethanol. This is ethanol, pKa 16. Okay, this is a stronger acid compared to acetylene. Acetylene is pKa 25. Therefore, it is a acetylene is pKa 25. That is a weaker acid compared to ethanol here. Therefore, in this reaction, that is acetylene reacting with the ethoxide. Now we have to see whether ethoxide is strong enough to remove the proton from here. Which the equilibrium will favor what? Which direction the equilibrium will proceed? Equilibrium always proceeds in the direction of the weaker acid or a weaker base here. Okay, now here pKa 25 means it is a weaker one. It is a weaker acid here. Compared to ethanol, the product is stronger acid, that is pKa 16 here. Okay, that is ethanol here. Therefore, it is a stronger acid. So, equilibrium favors the starting material here. Okay, it goes in the direction of, in the reverse direction. So, it is not favoring the formation of the products here. Correct. So, when it is not favoring the products means ethoxide is not capable or rather strong enough to knock out the proton from the acetylene. Correct. Acetylene is, now again I will explain. Here, you know that ethanol, the ethoxide is the conjugate base here. Okay, ethanol is a stronger acid, pKa 16. Acetylene is a weaker acid, pKa 25. Now, ethoxide is a weaker base. Then acetylide, the conjugate base of acetylene, is a stronger base here. Now, the reaction is between a weaker acid, that is acetylene, plus a weaker base, that is ethoxide. Ethoxide is a weaker base reacting with a weaker acid here. And the products formed here are acetylide anion, that is a conjugate base of acetylene. Okay, then we are getting ethanol. Ethanol here. Okay, now this conjugate base, so the equilibrium, it favors the starting material here. It means the base ethoxide, it is not strong enough to deprotonate acetylene. Okay, the base ethoxide, it is not strong enough to deprotonate acetylene. That is the reason the reaction is proceeding in the reverse direction here. Equilibrium favors starting material here. Okay, so base is not strong enough here. Now, let us see the other reaction here. Now, we have seen the reaction between acetylene and ethoxide. Now, if you see the reaction between ethanol and acetylide, okay, ethanol is a stronger acid here, acetylide is a stronger base. Now, let us see how the reaction will proceed here. I'll just change the page now. So ethanol, this is our ethanol, pKa 16. Okay, so this is reacting with the acetylide anion. This is our acetylide anion. Ethanol reacting with acetylide. Okay, now the reaction, let us see how the reaction will be proceeding. Okay, now what we will be getting here? Ethanol will give its conjugate base, ethoxide. Okay, this is the acid, this is the base here. So, ethoxide. This is conjugate base, ethoxide. Plus acetylene. Okay, this is acetylene. This is the conjugate acid, then pKa 25. So weaker acid. Okay, and ethanol is a stronger acid. Now let us predict the outcome of the reaction here. In which direction the reaction will proceed here. That is, a strong acid reacts with an acetylide, a base. It is giving a weak acid here. Therefore, equilibrium always favors the formation of the weaker product here. Okay, weaker acid here. Therefore, the first arrow, it should be a longer arrow here. Unequal equilibrium arrows, we have to put it here to indicate the formation of the products here. That is, the equilibrium favors the formation of the products. That is, the arrow should be pointing towards the weaker acid here. Here the weaker acid is acetylene. Okay, ethanol, it is reacting with the acetylide. Okay, it is giving a conjugate base ethoxide. Then it is forming acetylene. Acetylene pKa 25, it is a weaker acid. Therefore, the direction of the equilibrium is always towards the formation of the weaker acid or weaker base, whatever it is. Equilibrium favors the formation of the products here. Okay, now what does it mean? That is, acetylide, ethanol is getting deprotonated. This is called a deprotonation reactions here. Ethanol is getting deprotonated by acetylide. Okay, now acetylide is the conjugate base of acetylene. Okay, now acetylene is weaker than ethanol. What a point. Now, I will repeat, ethanol is, getting deprotonated by acetylide here. That is because the reaction equilibrium favors the formation of the products here. Therefore, ethanol is deprotonated by acetylide. Okay, now, what is acetylide? Acetylide is the conjugate base of acetylene. What is acetylene? Acetylene is an acid. Okay, now this acetylene, it is weaker than ethanol. Got the point? Therefore, an acid can be deprotonated by the conjugate base of any other acid having a higher pKa value. That is a weaker acid. A acid can be deprotonated by the conjugate base of any acid having a higher pKa value here. That is, the base acetylide here, it is strong enough to deprotonate ethanol. Okay. So, the base acetylide, it is strong enough to deprotonate ethanol here. That is, an acid can be deprotonated by the conjugate base of any other acid having a higher pKa value. That means higher pKa value means weaker acid. Okay. So I hope you have understood. So thank you very much for listening.